Yeah, just put it outside, don't get touch.
Okay, so sorry for the delay, but we can start. Okay, so last time we have arrived until this point in which we have tried to understand what is the mean power that is related to each speckle, okay? That are generated by the diffuser. Now, it is a good idea, I mean, to understand what I mean when I said that the diffuser completely destroy the spatial coherence of the source, okay? Because this number, more or less, is the number of speckles that you receive onto a photodiode at this distance and with this diameter, and that's okay. But if you try to understand what is the number of complete modes or speckle, this is the same thing, that are diffused back by the diffuser, then you have to use the acceptance of the diffuser, okay? So the area that you illuminate on the diffuser with your laser, multiplied by the solid angle of emission that is just pi, okay? And you have to divide this by the acceptance of the single mode. If you do this, you get a number that is definitely higher than this, okay? So you have 10,000, hundreds of thousands of modes, starting from one spatial mode, okay? So this is this is the real thing. I mean, when I'm saying that the diffuser completely destroyed the spatial coherence of the source, okay? So you start with just one mode, one single mode, spatial, and then you go on with hundreds of thousands of modes, okay? Now the question is, okay, in this situation, is it possible to do an interferometric measurement? And now we try to understand if this is possible using this setup. This is not a real one. This is a big difference with respect to what we are seeing with, for example, the double beam interferometer or the double frequency interferometer. That were real setup, real instrument. This is just a principle one, just to give you the idea that something is possible with a speckle pattern situation. Okay? In particular, we have seen, we can see a double frequency interferometer, and we have a lens here. Okay? This is the important point, because now we have to focus light onto the diffuser. Okay? To understand what happens, we can say that the diameter of the beam, of the incoming beam, is 2WL, okay? And that we have used a lens that has a particular focal length, okay? This is the situation. Now, first thing, let's suppose that the real situation is different from what you see from the slide. What I mean, that this distance, the distance between the, let's say, incoming beam and the outcoming beam is shorter, okay? Let's suppose this. In this way, we can try to understand, first, what is the radius of the spot onto the diffuser. Okay? Last time we have seen that if you use single mode radiation, you go onto a lens with a particular focal length. Okay? The radius in the spot, if you use all the lens, was given by, so let's call it R. That was given by the wavelength divided by P and divided by the numerical aperture of the lens. Okay? Now, in this case, the situation is a bit different because the incoming beam uses all the lens or not? Not. He uses just a part of the lens. Okay? So we can define, or we can write, that the radius of the spot will again be proportional to the wavelength divided by pi, but divided not by the numerical aperture of the lens, but the numerical aperture, let's say, effective. Okay? What is the numerical aperture, the effective numerical aperture of the lens? In an approximation, we can write this thing. So we know that the beam has a diameter that is 2WL. Okay? So we can say that the numerical aperture, the effective numerical aperture is simply given by the radius of the beam divided by the distance that is the focal length. Okay? So always remember this, if you have a particular lens with a particular numerical aperture, if you want the shorter spot, you have to use all the lens. This is the idea. Okay? Okay, this is the first thing. Now, another important thing is to understand what is, let's say, the maximum displacement of the target, okay, that keep the spot in focus. Because what happens for you, what is the real difference between a corner cube and a diffuser? If this object, the target, moves, let's say, too much, what happens in your opinion to the speckle distribution, to the speckle pattern distribution? Because you are focusing light here, okay? So if this target moves too much, the area illuminated on the diffuser changes, okay? And if this area changes, also, what does it change? It changes also the speckle pattern distribution, okay? This is important. So, as a first approximation, we can say that, let's call it the DLM, let's call it focus. Okay. This DLM focus is the maximum displacement, okay, of the target under which the spot remain more or less with the same size. And so, if the spot on the diffuser remain of the same size, the speckle pattern distribution is the same, remain unaltered. Okay? This is important. This is simply given by the depth of focus of the lens. Okay? We can say that this is equivalent to the depth of focus of the lens. We must be a bit more precise because, as I said, for the numerical aperture, we need to use the effective depth of focus of the lens. Okay? Because, again, I'm not using all the length, but just a part of it. Okay? In particular, if you have the radius of the spot, the depth of focus, the effective depth of focus, is given by this relation. We have WD divided by the effective numerical aperture. Okay? And so what does it mean? That we have lambda divided by pi divided by the square value of the effective numerical aperture. Okay? If you have ever tried to do a macro with your phone, you use a high numerical aperture. And if you see this, so the depth of focus is very short because you have a high numerical aperture. So what is in focus? Just the detail that you try to shot. Okay? All of the rest of the space is out of focus. So this is the meaning of depth of focus. Okay? The higher the numerical aperture, the shorter the depth of focus. Okay? Okay. So we have understand that in this condition, the speckle distribution that is diffused does not change. Okay? If we limit the movement of this object to this distance, the speckle pattern distribution does not change. Now, the other question is, how many speckles are here? Okay? How many speckles do I see here? Because all of these speckles will overpose to the reference beam that is still single mode. Okay? In your opinion, what is the perfect situation? It is good to have a large number of speckles or just one? To be able to do a correct interferometric measurement. It is good to have just one, okay? Because in this way, since we know that area of the space that is the area of the space that is contained in a speckle is an area in which the electric field has a correlation that is higher than 0.5. Okay. So now, since we want to do an interferometric measurement, we are interested in the phase relation between the field, the measuring field, and the reference one. Okay. So if we have just one speckle and the target moves, okay, we have the possibility to do an interferometric measurement, because here we will have a speckle that moves, okay, and the phase inside the speckle will remain, let's say, without jump, okay. All the contribution will be correlated to each other. So this is a good point. And another thing that I have not said, so I said it now, if the target moves of just the depth of focus, it is the situation that happens, it is like that the speckle are dragged from the target, okay? So imagine the situation. You start from a situation in which the target is at rest, is still. Then it starts to move. But it moves not too much. I mean, the maximum displacement is the depth of focus. In this case, we can say, this is just a qualitative discussion. But what happens is, more or less, that if you have a cigar here, so a speckle, then it moves with the target. And in this sense, it is good to have just one speckle, because you have a particular phase of the reference field, and then you have to compare this field with the phase, you have to compare this phase with the optical phase of the speckle, and then if you have a situation like this, since you know that here the field is correlated, then you can do an interferometric measurement. Okay? Now, what is the procedure to understand what is the transversal dimension here, in this part? Then we can suppose that from this point on, the rays are collimated, okay? So this is more or less the idea. The transversal dimension is always given by the general formula, the correct one, that say that this dimension is proportional to the wavelength, the distance from the diffuser and the diameter of the spot onto the diffuser. Okay? So we can write, remember, we work in the approximation in which these two beams are close. Okay, this is the approximation that I'm using. So, in particular, Z became, the focal length. Okay? And the diameter of the spot on the diffuser is simply given by 2W, what I have said, WD. I don't remember. W. But when I say this, W is equal to lambda divided by pi NA effective. What I said? D. Okay, thank you. Okay, this is the situation. And, okay, let's go on, because we have the wavelength, the focal length, then we have 2 lambda divided by pi NA effective, okay? But if you recall that the effective numerical aperture is given by, okay, so we have lambda F divided by 2 lambda multiplied by pi L divided by F. Okay? It should be correct. Then we can simplify something. And then we have pi divided by 2 multiplied by the radius of the beam, of the incoming beam. Okay? This is a very good result, and it's simply given by the fact that we are using a lens. Okay? Because what does this result say? It says that the transversal dimension, remember that when I say the transversal dimension is the radius of the speckle, okay? This is not the radius, it's the diameter, not the radius, okay? So, this is given by pi divided by 2 WL, and the diameter of the laser is 2 WL, okay? So you have just one, well, a bit more than one, let's say, speckle that can be overposed to the reference field, okay? And this is a great result, okay? Because if you do the ratio of 2 WL divided by 2 WL, what you get is 4 over pi. So this is a bit more than 1, okay? And this means that you have a full speckle that can be overposed to the reference beam. The real situation is not like the one that is depicted here. So this dimension, the useful, let's say, dimension, is a bit more shorter, or it's a bit more little than the reference one. Okay? But this is a very good point. Well, a very good situation. Because now, if we look into the slide, when we work with the speckle pattern distribution, we have a new source of noise, let's call it in this way, that is related to the speckle pattern distribution. Okay? This new source of noise, again, I give you just the result because the full treatment is very hard, very difficult. Because, as I said last time, if you want to have the full treatment of speckle pattern interferometry, then you have to go with the statistical approach. So it is a bit hard. You can define a new noise equivalent displacement that is related to a longitudinal displacement of the diffuser, and this NED, NED, is proportional to the wavelength and to the ratio of DLM, I would like to suggest that I want to limit the movement to the DL related to the depth of focus of the lens. And then we have to divide this by the longitudinal dimension of the speckle. So what does this relation say? That the noise equivalent displacement is very low if this quantity is definitely lower than the longitudinal displacement, sorry, the longitudinal dimension of the speckle. Okay? So it can work. You can have an interferometric measurement because we have seen that just one of the speckle overposed to the reference beam. This is the first point. Then you can do a very precise measurement if you limit the movement of the target. Okay? And this is the idea. Okay? Here you have the scale factor, because I said proportional because here there is a constant that is more or less equal to 1, so it's not important. But the important thing is that the noise equivalent displacement is related to the wavelength and to this ratio. So the lower this ratio, the higher the resolution, okay, or the limit of measurement. This is important. We can try to use some number just to understand if we can have, let's say, good measurement or not. Not good, it's not correct. Useful measurement or not. Okay? For example, if we work with a radius of the laser beam that is 50 micrometer and with a lens that has a focal length of 1 centimeter, or let's say 10 millimeter, then what we have? Okay. For example, let's look at what is the depth of focus of the lens, the effective depth of focus of the lens. And we have already written, but anyway, I will rewrite. This is lambda divided by pi numerical effective aperture squared. So what you get is 8 millimeters, okay? Not a bad distance, especially because you can work in a situation in which this limit is very low. How can you evaluate this limit? You have to evaluate also the longitudinal dimension of the speckle, okay? And in particular, the longitudinal dimension is given by this relation. This is 2z divided by d, and this value is squared, where again z is the distance from the diffuser, and d is the diameter onto the diffuser. So we can approximate this relation with lambda multiplied by 2f divided by the diameter is simply given by 2wd. And we have to square this quantity. Okay? In the starting condition, we have that this quantity is equal to 39 millimeter. Okay? And so what we get is that the NED speckle is given by the wavelength divided by by the ratio of dz m dl m focus. And so what we have, lambda multiplied by 8 divided by 39 And here we have 1 over, let's say 1 over 5, more or less. So we have the wavelength divided by 5. This is more or less 100 something, 120 nanometers. Okay? Okay, this could be good, but let's say, because now we want to measure, we say that we limit the dynamic range of measurement, of displacement of the target to 8 millimeters. So in this condition, we can measure this 8 millimeters, let's say, vibration, okay, of the target with a resolution, a minimum resolution of 120 nanometers. It could be fine, but we can do something more. We can do something better if we change the operation, the working condition. So let's suppose that now we use a WL star that is equal to 100 micron. So we double the dimension of the beam. If we double the dimension of the beam, in your opinion, what happened here to the dimension of the spot? What is the idea that I am trying to follow? Why it is good to increase the dimension of the beam? Because if you increase the dimension of the beam, what happens? That you decrease the dimension of the spot onto the diffuser. Okay? And this is, in general, always good when you work with speckle pattern. So, you have a new longitudinal dimension, the formula remains unchanged. Of course, you have a new WDS value, the formula remains unchanged. And then you have more or less 156 millimeter, okay? Then you have also another value for the depth of focus of the lens, the effective depth of focus of the lens. In this case, you get 2 millimeter. And so the new noise equivalent displacement of the speckle is given by the wavelength divided by 2 over 156. Okay? And in this case, we have more or less 8 nanometer of minimum, let's say, measurable displacement. Okay? We gained, let's say, something in noise equivalent displacement term. Okay? We can be definitely more precise. What we have lost here in this calculation? Because we have lost something. We have lost something here in what is the maximum displacement of the target. Okay? Before it was 8 millimeters, now the maximum displacement is 2 millimeters. But we have gained in possible resolution. Okay? So keep in mind this trade-off, let's say. Okay? The important thing to point out is that even with a let's say principal setup or principal instrument that uses just one lens, we have understood two things. The possible displacement of the target that does not change the speckle distribution can be in the order of millimeter easily. So it seems, let's say, a low value millimeter, but when you want to measure something with sub-nanometer resolution, this is not a low value. Okay? We have seen another point, that the optical system filters itself the number of speckles that can be overposed to the reference beam. So we have just one speckle that can make the interferometric measurement. This is good. And we have seen that we can have, with, let's say, real-world situation, working condition, very high value of resolution, easily. Okay? This is important. Now, if you go from a principal scheme to a real one, what are the errors that can be related to the speckle pattern? Now, the first point is intensity. Because if you remember, we have seen that if we put ourselves on an orthogonal plane with respect, or a parallel plane with respect to the diffuser, the intensity distribution of all the speckles that we can find onto this plane goes, let's say, with the probability density function of intensity, that is better to say, of the intensity of the speckle is a negative exponential. Okay, so what we have to understand that the probability to find, let's say, a dark speckle or a speckle that has an intensity that is lower than the mean value is higher than the probability. This probability is this area. Okay, is lower than the probability to find a speckle, or let's say a bright speckle, that has an intensity that is larger than the mean value. Okay, so we have this problem. This problem means that the power that is related or associated with a speckle is generally lower than the mean value, okay, or in general very low. What you can do? A possibility is to use a better focusing of the laser on the target, as we have tried to do before. When we have doubled the dimension of the beam, we have focused the light better onto the diffuser. So this is a first point. We can have a duplication of receiver, okay? So we have two photodiodes that are able to build up an interferometric signal. If we have just one, the probability to get, let's say, dark speckle is higher than if we have two photodiodes. Okay? With the second one, it is more probable to work with a bright speckle. Or, and Michele is the ideator of this idea. Michele, no, I don't know if you know Michele, because there is another technique. So, instead of trying to move a bit the instrument with respect to the wall, for example, in order to find out a speckle distribution for which the speckle that is coming, or better, the speckle that is overposing to the reference field is a bright one, okay? You can try to move just, this lens a bit. No, this lens is not correct. Sorry, the laser beam. Because if you now move a bit the laser beam, no, you don't change just the diameter of the beam, but you move it, you can illuminate different zones of the wall, okay? And again, in this way, you can change the speckle pattern distribution. So you can do this, you change the position of the source until the speckle that is doing the interferometric measurement is a bright one. Okay? This is the idea. Okay, this is what we have said. This is what you can see here in the definition of the noise equivalent displacement. Let's say the closer the movement of the target is with the longitudinal dimension of the speckle, and then the higher the phase error related to the measurement. Okay? This is important, because if the maximum displacement is equal to the longitudinal dimension, then you commit an error that in phase is equal to 2 pi, in wavelength is equal to the wavelength. Okay? Even this tells you that it is important to limit the longitudinal displacement with respect to the longitudinal dimension of the speckle. Okay? So the consequence of all this consideration tells you that it is not possible to build up an incremental instrument, as we have said with the double beam interferometer, the double frequency interferometer, but we can build up an instrument that is able to measure very small displacement, or better, displacement that are shorter or lower than the longitudinal dimension of the speckle. So this configuration is perfect to develop a vibrometer. So an instrument that is able to measure vibration of an object with respect to a rest position, okay, or to a zero position. Okay, so in a usual condition, when we have corner cube or reflective target, we can build up instrument that can measure very large displacement, okay, with very high resolution. In this case, we can still do measurement with very high resolution, but the problem is that we are limited in the dynamic range of displacement. And so this is the perfect condition to build up a vibrometer. Okay?
Sorry, in the last condition where you move a little bit the laser beam, you do it once and then you leave it where it's done?
If this condition is satisfied, yes. Yes.
It means that you are working at fixed distance.
Yes, of course. For example, imagine a loudspeaker. Then we want to characterize the loudspeaker. Okay, the loudspeaker is the easiest, say, target that vibrates. Okay, so you put the loudspeaker at a certain distance with respect to the instrument. Then you move a bit the laser, but in this direction, so not in this one, until you get a speckle distribution that gives to you a bright speckle. Then you can start to do the measurement, and if you limit the movement of the loudspeaker, you are good. You don't have to do anything more, okay? Okay. With a complication in the instrument, you can even go a bit farther than this, okay? But it's a complication. I want just to give the idea that the measurement is possible. And now we can change the argument, and then we can go to self-mixing interferometry. Okay, just a second. I hope just 1 second. Devo cambiare sto computer.
Ma usi il visualizzatore invece di PowerPoint perché è più leggero?
Perché è gratis, perché è più leggero anche.
Ah, è gratis, PowerPoint si copia.
Sì, questo è anche vero. Beh.
Perché col PowerPoint li puoi aprire anche 5 file prima e poi passi da uno all'altro. Così devi aprire e chiudere. Se lo doppio clicchi hai anche un PowerPoint sul PC?
No.
No, non lo puoi aprire. Però è associato a qualche applicazione, forse è associato
al viewer.
Magari con doppio clic gli funziona meglio di come stai provando ad aprirlo ora, anche se in teoria è la stessa cosa.
Ma di solito se fai il doppio clic ti dice non hai PowerPoint, quindi non te lo apri.
Ah, salva con nome.
Ma che cavolo sta succedendo? Scusate, È tutto a posto, non c'è altro. Si è impastato. Si è impastato il PC. Sì, per forza. Facciamolo alla portata. Bene. 15 anni in effetti. Ma secondo te funziona il Bluetooth con questi proiettori nuovi? Perché sennò basterebbe il cellulare.
Forse, non lo so.
Io su alcuni l'ho
La gente
fatto.
usa il cavo, non so se sono wireless.
Perché col cellulare sarebbe ancora più comodo, però. Sorry for this delay. But let's say shit happens. Okay. Oh, okay. So we can start. Okay. A quick review on what we have seen as the readout configuration of interferometry. What we have seen until now is this. We have an interferometer that is outside the laser cavity. Oggi è un disastro. Okay, so we have, for this reason, let's say, this is called an external configuration, okay? And what we see, we read the, let's say, optical phase differences between the reference beam and the measuring one, looking at the intensity or at the modulation of the intensity of light, okay? This is what we have seen until now. There is another possible configuration that is the internal one. What does it mean? That now the laser itself, okay, can have internally the interferometer, okay? In this particular way, in this particular situation, this is what we can find, not exactly this setup, but more or less the same, in the ring laser gyroscope, okay? And what we have, let's say, one mode is sustained by the cavity that is composed by the back mirror of the laser and the reference mirror. So this mirror is fixed. Okay, so the mode that is sustained by this cavity is at a fixed frequency. Okay, good. Then there is the second mode that is sustained by the measuring, let's say, cavity that is composed by the moving mirror and, again, the back mirror of the laser. And then the frequency of emission of this mode can be changed by tuning in position of the moving mirror. Okay? Then what you get onto the photodiode? Onto the photodiode you have a signal that has a carrier that has a frequency that is given by the difference of the two modes. This is more or less what we have seen in the double frequency interferometer. Now, the frequency of this signal, or of the photodetected current, or of this carrier, changes if this mirror changes its position. Okay? Now, in particular, what we can write to understand what happens, it is easy to understand that let's say that the variation in displacement of the moving mirror can be related to the change in frequency between the two modes as what? In your opinion, if we use this setup, I say that if I move this mirror, the frequency of the mode changes. Okay? But what is the maximum displacement of this mirror to avoid ambiguity in mode selection, let's say, or in mode consideration? What is this cavity? This is a Fabry-Perot cavity. Okay? So what do we know? We know that if the moving mirror moves of lambda over 2, of half of the wavelength, we can jump onto the next mode, longitudinal mode. Okay? If we move farther than lambda over 2, then we can have an ambiguity, because what mode are we considering or selecting? So the maximum displacement is related to lambda over 2, and what is the maximum change in frequency for a displacement of lambda over 2? We have one mode jump, so we have the maximum frequency that is given by C divided by 2L, where L is the length of the element, in this case, is the length of the cavity. Okay? In particular, what is really important is the sensitivity or responsivity of this in frequency of this instrument that is given by the inverse of this. So it is dmi divided by the Lm. And if you work with a, let's say, measuring cavity that is 20 centimeters, that is very easy to achieve with a EMA laser, what you get is a tremendous resolution, because it's true. You are limiting the displacement to lambda over 2. This is true. But the resolution is 2.4 megahertz of change in frequency difference between the, let's say, reference mode and measuring one, divided by nanometer. So for each change in displacement of 1 nanometer of the moving mirror, you see a change in frequency of 2 megahertz. So you with a, let's say, every kind of oscilloscope, you can go definitely down the nanometer displacement, and you can still see the change in frequency. Okay? So this setup is used when you want to measure very tiny displacement of the moving mirror with a very high accuracy. And you already know that the total displacement will be limited by half of the wavelength. Okay? In a way, this limitation, or the fact that the maximum displacement is given by lambda over 2, is not a problem, because you already know that if you use this setup, the variation that you want to measure will be more or less in the range of nanometer or sub-nanometer. Okay? And then you have a third possibility, that, let's say, that is the easiest one in terms of component that you want to use. This is the self-mixing interferometer. What you have? You have, again, of course, a source, and in this case, this is a particular case of an external interferometer, because you have just one mirror. This is the moving mirror, okay? So let's suppose that the moving mirror is at a fixed distance from the output of the laser, and let's suppose that this mirror is vibrating around a quiescent distance that is S0, okay? So you have emission of the unperturbed field, then you have propagation in the external cavity, and then here you have the value of the back reflected or back diffused field. Then, instead of what we have done with Murchison interferometer, you allow this field to re-enter the cavity. Of course, not all the field, but just a part, because you have the transmission, the power transmission of this mirror. Okay. And then what happens inside the laser cavity? Inside the laser cavity, you have, again, an homodyne coherent scheme of detection. Okay? Because, let's say, the optical frequency is the same, What changes is the amplitude and the optical phase. Okay. So, if you have this coherent scheme of detection, you can still work at the quantum limit regime of detection. That was, you already know, a very good property of interferometry. Interferometric instruments, sorry. Okay? In particular, since now here inside the laser cavity you have overposition of the unperturbed field and of the reinjected field, what happens is that now emission of the laser will be modulated both in amplitude and frequency. In particular, this is a sketch of what happens inside the laser. You have that the component along the direction of the unperturbed field gives to you the amplitude modulation, and the component that is in quadrature with respect to the unperturbed field gives to you the frequency modulation of the signal. Okay? And this is something that is very important because this is happening inside the laser. Okay? Since you have allowed a part of the electric field to re-enter the cavity, now the emission is not, let's say, continuous. You don't have a continuous wave emission, but the amplitude and frequency of the laser is changed or changes. Of course, changes if this mirror moves. Okay, you have this modulation. And the very good point is that you have an amplitude and a frequency modulation that are dependent, one, from the cosine of the optical phase. Here, the optical phase is easier because we don't have a reference beam or a reference path. We just have the external cavity length. Okay? So the optical phase is easier than what we have seen until now. And as I was saying, the amplitude modulation is proportional to the cosine of the optical phase, and the frequency modulation is proportional to the sine of this optical phase. So you have two signals in quadrature, okay, that you can use to measure the displacement, let's say, a vibration of a mirror or a displacement or longitudinal displacement of the mirror without ambiguity on the sign of movement. Because you already are in the situation of the double, let's say, beam interferometer, in which you have sine and cosine of the optical phase. Okay? This is just simply related to what happened inside the cavity. Okay? And this is very important because I want to point out it immediately. What is the real meaning of you have changed the way of emission of the laser? What does it really mean? That if you want to do a measurement of this kind, you can put the photodiode not just here, but anywhere in the beam. Okay? What was happening in the Manchester interferometer, for example? The photodiode could be put just on the output of the instrument, because you have to get the overposition of the reference and measuring beam. Okay? Now you can put the photodiode even onto the moving mirror. Okay? Because what is changed is the way of emission of the laser. You physically have changed, the way of emission of the laser. Okay? This is very important and big differences between this configuration and the other one. Okay? Because in the other configuration, you were trying to avoid reinjection of the electric field into the laser cavity. Okay? Now you avoid this. Now you permit this, and so this changes the game, let's say. So first realization of this of a self-mixing interferometer was done by Donati. This is the scheme of Silvano Donati. Now, you are using a Heine laser, a particular, let's say, Heine laser, because you use also a magnetic field. So you use another sort of Zeeman effect. Okay? In this case, the magnetic field is not longitudinal, but it's transverse to the laser cavity. If you do this, the Heaney laser emits on two linearly polarized orthogonal orthogonal modes. Okay? And mode separation is more or less close to 100 kilohertz. Okay? Now, why you use two modes? Because one will be used as a reference mode, and the other one will be able to go into the external cavity until the target. Okay? In particular, the two orthogonal modes will be one directed as the magnetic field. So, for example, one will be planar to the slide, okay? And the other one will be orthogonal to the slide. Okay? Now let's suppose that you that mode 1 is forced to remain inside the cavity, or let's say not to go into the external one. As you can do, what is the way to do this? Use a polarizer here, okay, that block one of the two polarization. In this case, since we have a polarizer that is directed orthogonally, the reference mode is the one that is planarly polarized. Okay? So, the mode with orthogonal polarization with respect to the slide is able to go into the external cavity, and it is the mode that will be frequency and amplitude modulated. Okay? That we will see, let's say, the frequency and amplitude modulation. Then what you do, since you have two optical beam at optical frequency, but the difference of this optical frequency is more or less 100 kilohertz, you can, with a second polarizer that is at 45 degrees with respect to the mode 1 or mode 2, this is mode 2 and this is mode 1, okay? You can take part of both the beam, and then you can down-convert the amplitude and frequency modulation that the second mode will see onto a carrier that is at a frequency that is more or less close to 100 kilohertz. Okay? You pass the amplitude and frequency modulation of the optical mode 2 to, let's say, an electrical carrier that is at the frequency of 100 kilohertz. So this is why it is useful to have a reference mode that is not going outside, so that is not going into the external cavity. We use this just to have a down conversion on frequency and amplitude modulation to an electrical carrier. Okay? Another point. We are doing the measurement over a loudspeaker, directly onto a loudspeaker. So we are working with a speckle pattern distribution. Okay? Before going on, let's see. Okay, we are using a speckle pattern. We are working with a speckle pattern distribution. So now, what happened to the number of speckles that are emitted to re-enter the cavity? Okay? First thing, since we are using a Heaney laser, what we know? That we have a beam waste at the output, so on the output face or mirror of the Heaney laser. And what we know? We also know that, let's say, the angle of divergence of light that is emitted is given by lambda divided by pi W0. Okay? So now, what is the diameter of the spot onto the diffuser? What is the diameter of the spot that you illuminate, with which you illuminate, let's say, the loudspeaker? This is simply given by 2. Let's suppose that you work at a distance S0 from the output mirror, or let's say that the quiescent position of the loudspeaker is at a position S0 from the output mirror of the laser. So what you have 2 theta L multiplied by S0. Okay? Now, what is the transversal dimension of the speckle that you will find back onto the output mirror? Okay? Because now you have understood what is the dimension of the spot onto the diffuser. And you know that if you know the diameter of the spot, you can evaluate the transverse dimension of the speckle. This is given by lambda, multiplied by the distance that in this case is still S0, and divided by the diameter of the spot. Okay? So, let's go on. What we get? We get lambda S0 divided by 2 theta L S0 and theta L, so we have lambda S0 multiplied by pi W0 divided by 2 lambda S0. So what you get, it seems a magical situation, but what you get is that again, of all the hundred of thousands of modes or special modes that are now back diffused by the loudspeaker, just one will be overposed to the unperturbed field inside the cavity. Okay?